All right, now that we know how atoms are constructed, we know that they have protons and neutrons in the nucleus, and they have atoms orbiting. If you remember way back in the beginning, we said that electrons are what determine the reactivity, how an element reacts. And a lot of that has to do with where they are in an atom. That's called orbitals. So we're going to start from the very beginning. So here's what happens when we start trying to put objects with different kinds of charges together. We know that if you try to put two like charges next to each other, we know that they repel. It's just a thing that they do. But if we were to try that with two charges that were opposite, they attract. Let me make that bigger. Well, that's too big. Sorry about that. So we know that opposite charges repel. Well, that starts to be a problem when you have atoms like, here's our buddy carbon. We know carbon's got an atomic number of 6, which means it has 6 protons, and of course that means it has 6 electrons. Or oxygen. Oxygen's got an atomic number of 8. That means it has 8 protons, and that means it has 8 neutrons. Or what about a big element like tungsten? I mean, it's not only Mr. O's favorite element, but this is a big, heavy-duty element here we're talking about. This has got an atomic number of 74. That means it has 74 protons, and that means it has 74 electrons. Well, that's a lot of electrons. And you have to keep in mind that if they're going to be repelling each other all the time, we have to put them in a certain area around the atom where they don't repel. Ladies and gentlemen, that is what orbitals are for. And so, where we put electrons around an atom depends on where it is in the periodic table and how many electrons there are. So let's get to it. So we're going to start by saying that this common model of the atom that has been in the use since the early 1900s is wrong. So we're going to completely ignore this model. Anytime you see it, you'll know that you have a superiority because you know that this is not how an atom really works. How does it work? It turns out that they work like this. They don't just orbit the nucleus. All right, they can't, it's not that here is an electron and it orbits the nucleus and you can find it anywhere along this distance from the nucleus. It isn't like that. The way it works is that they are found in areas. So this is one area that we could expect to find an electron. Here is another area that we could expect to find an electron. Here is one. They're kind of like floors in a building. And I can't draw very well, so this is what I'm shooting for. This is what we mean by energy levels. They are if I zoom in here, they are a definite distance from the nucleus. And there's no in between. An electron can exist here or here, but it can't exist in the middle. We're going to think of these like floors in a building. I'll show you what I'm talking about. So energy levels in an atom are like floors in a building. The higher up you go, the more energy you have, because the more work it takes to get all the way up there to the 12th floor. And whatever you bring with you has energy too, because if you say you decided to drop a watermelon out the first floor, it wouldn't really do much damage. But if you dropped a watermelon out through the 12th floor, it's going to do some damage to whatever it hits. Well, energy levels in atoms are the same way. And the higher up you go, the more energy you have. But unlike floors in a building, the higher up you go, the more room you have. So, if energy levels are like floors in a building, then orbitals are the rooms. So if we look at a floor plan of any building, you'll notice that some of these rooms have different shapes, and some of them are facing different ways. And no matter what, our rooms in our floor of our building can hold a total of 2 electrons, and that's it. And the higher up you go, the more room you have, and the more electrons you can hold. Here's what rooms in an atom look like. So these are what orbitals, or the rooms in an atom, look like, and they sure are a funny shape. And the reason why they're shaped so weird is because they're designed to prevent electrons from repelling each other. So we're going to get into how these work. We'll start on the first energy level, and often we'll abbreviate energy level with this lowercase n. So whenever we see a lowercase n, that means energy level. And here we are on the first energy level, and we're on the first floor. And so there isn't much room, and there's only one type of room available, or orbital, to put our electrons in. Here's what it looks like. It's spherical. So for short, we call the S. So when we're at energy level 1, on the first level, there's only one type of orbital available. It's an s orbital. And because it's on the first energy level, we'll call it the 1s. And this can hold a total of 2 electrons. And electrons will stay in the same orbital as long as they're spinning in opposite directions. So we can say that this orbital holds 2 electrons, and we'll say as long as one is facing one direction and the other is facing in the opposite direction. We'll call this one an up electron, and we'll call this one a down electron. Okay, let's go to the second energy level. Now we're on the second energy level, n equals 2. Because we are higher up, we have more room, and that means we've got more space. So we have an s orbital, and of course it is spherical, just like the one in the 1 energy level, but it's bigger, right? Here is our 1s, and here is the 1s here. And of course the nucleus is in the middle because all these electrons are orbiting the nucleus. But at the second energy level, we have more room, and we have an S-shaped orbital that's even bigger. So we have an energy level that is, we're on the second energy level, we have an orbital that is S-shaped, so we're going to call that the 2s, and it can hold 2 electrons. But at the second energy level, we've got more space, and that means we've got room for more electrons, and that means we have to start getting creative. So because we've got more room, we've got more space for electrons. And that means that we've got to come up with a different type of orbital to hold them, a different type of room. But it has to look different than the sphere shape, because if it was the same shape, then they would all hit each other. We can't have that. So it's got to look a little funny to stay out of the way. And it looks like this. Okay? This is the second type of orbital available at the second energy level. It's called a peanut, or P for short, and it's at the second energy level, so we'll call it the 2p. But it's not a sphere, which means you can do different things with this orbital than you can do with a sphere. For example, because the p orbital is shaped like it is, it's three-dimensional. In other words, you can point it in different directions. You can't point a sphere in different directions, but you can point these all different directions. And if you laid them over each other, you'll see that they don't interfere. And even though they're funny looking, they can each only hold 2 electrons. So when we are at the second energy level, n equals 2, There is an s orbital available. We'll call that the 2s, and that can hold 2 electrons. And there are also 2 p orbitals available, and there are 3 of them. There's one p orbital lying on its side. We'll call it the 2px. There's one p orbital kind of lying the other direction. We'll call it the 2py. And there's one p orbital that's kind of standing straight up and down. We'll call that the 2pz. And each of these can hold a total of 2 electrons. So at the second energy level, because we have more room, we can hold a total of 8. Okay. We've been on the first floor, we've been on the second floor, and now we're going to go up to the third floor, where n equals 3. At the third energy level, we've got even more energy, and that means we've got more room. Our orbitals are even bigger. Here's what the 1s looks like. At the first energy level, the second s orbital is exactly the same shape, but bigger. Well, now we're on the third floor, and that means that our 3s is even bigger. That even though it's bigger, the 3s can only hold 2 electrons. Also at the third energy level, we have p-shaped orbitals, and they're bigger. Here are the 2 p's that were available at the second energy level. Well, the 3 p's look just like that, but they're bigger. There's also 3 of them. There's the 3px, the 3py, the 3pz. They're all the same. They are just pointing in different directions, and they can each hold 2 electrons. Well, the third energy level has got even more room. So at n equals 3, we've got a 3s that can hold 2 electrons, and we've got 3 3p's, and they can each hold 2 electrons. But we've got a new type of orbital available. It's called the double peanut, because it's kind of shaped like 2 peanuts. And what's cool about this shape is that it's even weirder, so you can do a lot of different things with this one. And because this one's so weird, there are 5 ways to arrange this so it stays out of the way of all the others. We're not going to try to worry about what direction they're pointing. We'll just say 3D1, 3D2, 3D3, 3D4, and 3D5. And no matter how weird looking they are, they can each hold 2 electrons. And that's it. Okay, you're ready to go to the last floor? Ladies and gentlemen, are you ready for the 4th floor? Last one, I promise. So here we are on the 4th floor. We've got even more energy. Here's our 1s, here's our 2s, here's our 3s. Well, our 4s orbital is even bigger. And we've got p-shaped orbitals, and they're bigger than the 3p or the 2p's. And they can each hold 2. We also have d orbitals at the 4th energy level, and they're bigger. See the smaller 3ds in there? Well, the 4ds are even bigger. They're way out there, and there's 5 of those. But we are on the 4th energy level, n equals 4. That means we've got more room, and that means that we need to come up with a new type of orbital that's even crazier looking than the first 3 types, so that we have a place to stash all of the electrons we now have room for. So, are you ready? This one's weird. We're going to call this the flower orbital, even though it doesn't look anything like a flower, but that means we'll call it the F orbital for short. And there are 7 ways to orient this. We'll call this the 4F1, 4F2, 4F3. It doesn't really matter. We're never going to look at these individually. 4F5, 4F6, and 4F7. And they can each hold 2. So despite how weird looking they are, that's as much as they can hold. So here's the recap. Each orbital can hold a total of 2 electrons as long as each one is spinning in the opposite direction. At energy level 1, we have only the 1 s orbital, and it can hold 2. Energy level 2 has got a 2s and 3 2p's. They can hold a total of 8. Energy level 3 has got a 3s, 3 3p's, and 5 3d's, and they can hold a total of 18. And finally, at the 4th energy level, when n equals 4, we have a total of 1 4s, 3 4Ps, 5 4Ds, and 7 4Fs, and together they can hold 32.